Yeah, I already shared with you the set of slides. You will find it now under module week 5, whatever, you will find the project, which is basically the recorded video of whatever we discussed, and also find a PDF, which we're gonna discuss today. Okay.
Yep, the slides are there. Thank you.
You're welcome. Okay, now I'm just allowing the rest of you guys, then we can stop. It's already recorded now. Let me just like share my screen so we can start talking. Everybody can see my screen?
I can.
Yeah, I can see it.
Okay, perfect. So anyway, I will keep allowing people, but I can start now. Okay, guys, so this slides in the beginning, it was designed for people to understand Verilog, and all of you took Verilog, right? So consider the first part of this slide is just reminding you how the Verilog work, especially for these people who are going to build like a RISC-V, or I mean, you're not going to build anything, you're going to just pick it out from internet and just deploy it on the FPGA chip. But look at it if there is something you need to fix, like porting the data and so on. So see all of this, I'm passing because it's just a Verilog, right? Up to here. Can you see my can you see the sign I made here?
Yeah, I can see that.
So yeah, look at the slides now into the parts. This is basically like giving you example about chapter 1, right? Because we're gonna have on Monday exam, right? So hopefully I will be fine by Monday. I think by Monday I can come to the campus. So I will be on campus on Monday. I'm gonna have a quiz. You guys know that. How the quiz it will be, I'm gonna be loading the exam on Gridscope. Then we will be using the time of the whole entire class on Monday for you to solve your the problem that I will give it to you in PDF, and then it will be loaded into the Gridscope. That's it. I'll grade it in a Gridscope. Automatically, it will send you the grade with all of the details about how did you get this grade. And then within you have 4 days maximum from the day of announcement to tell me that I found something I need to discuss with you. But if you come out of this 4 days and tell me, oh, let's say that you came before the final by 1 night and say, oh, why I took this grade in the question number 1 in quiz number 1, I will not ever reply, because you passed the midterm 1 and midterm 2 and quiz 2, and now you remember quiz 1. That makes sense. So maybe I can refine again. Monday, we're going to have a quiz. The quiz will be, it will be based on what? I'm going to create something, it's called Gridscope portal. A copy of the exam will be in a PDF, and Word format will be loaded in a module called Quiz 1 under Canvas. You guys will pick it up. You start solve on the PDF. Then you will take the PDF and you load it into the portal of the Gridscope. So that means, perhaps in the weekend, you guys will get like a message say that, Professor Ali created Gridscope, whatever, just accept it, And then, you will load it there. So you have to do all of this process in 1 hour, 15 minutes of the course. And I will meet you on there. There is no way for you to take this exam at home. You have to take this exam while you are in the class. This is the university policy. Sounds good? It's not my policy, by the way. It's the university.
Professor?
Yes.
I just had a quick question. So like, just to clarify, we will be having in-person class on Monday, correct?
We will have in-person class on Monday, yes. Based
Okay.
on the regulation, you know. I have to tell you, you know, I'm sick and I cannot be on person with you. That's all I until
Okay.
Monday.
I understand. Thank you.
You're welcome. I mean, for your safety, that's why I'm not on campus. Just taking all of the precautions so you guys will not get sick. Okay. So anyway, is it clear? So once, you know, you will load the thing, the quiz is done, you know, I have another 4,300 people, and I have 3,300, and I have 3,300 lab, and I have 10 master students, and I have whatever. So you will give me some good time so I can grade all of you, because, you know, I have almost 150 students. So I have to grade all of you. Then, you know, after that, you know, you guys will look into a grade. Your grade looks awesome. You have 4 days maximum from the day that I release your grade. You love it. Okay, perfect. You have a question within the 4 days. Day 5, you came with question. I'm sorry. So you have to be careful with that. That makes sense? Why I'm doing this? I'm human, and all of you guys are humans. So, you know, we are humans. That means we are limited in energy, right? So, you know, I wish I can have infinity energy and I help everybody. That makes sense? Okay, now for the quiz is the chapter 1. You already have homework 1 covered the chapter, right? I already give you the right answer for the homework 1. Look at it, read all the slides. And now I'm giving you more examples for chapter 1 so you can get the sense how the quiz will look like. Okay, so for instance here, right, example of how to calculate CPI. That's in a question, right? So you have a table in front of you of a program running, right? And this program has some of the instruction running and load and store and branching. So the whole entire program, 50% of it was some instruction talking to the ALU. And every single one take 4 cycles at a time. For the load, for instance, 30% of the whole entire program was loading data from the memory. And every time you load, it takes 5 cycles. And for the store to them into the memory, it's actually 5% of the whole entire program. And it's taken 4 cycles. And, you know, controlling like branch equal or not equal and all these things is around 15% of the whole entire power of the program. And every time you do that, it will be 2%. Calculate for me the CPI. Very straightforward, right? Why? Because you're gonna multiply, right? So this 50% is 0.5 times 4, 30% is 0.3 times 5, 5% is 0.05 times 4, and 50% 0.15 times 2. You multiply, you accumulate, and they're gonna be what? 4 cycles per instructions. Sounds cool? Very straightforward. If you get something like that, this is the right way to answer this question. Another way, right? Look, instead of making table like that, right? I'm telling you, consider an implementation of the MIPS. MIPS is what? ISA. What does it mean, ISA? Instruction set architecture. Do you agree? Any processor in the world using clock or not?
Yes, it is.
Yes, that means it has a crystal, right? Why the processor has a crystal? My question for you. What does it mean, processor? Somebody can tell me.
So it has a crystal so that it can keep track of the time or the clock, and processor just process the information, right? Or like the bits.
Exactly. And, you know, architecture-wise is bunch of sequential and what? Combinational circuit. Sequential, you need a clock. That's why you need a crystal to feed the sequential with clock. Right?
Yeah.
So the crystal here is producing 500 megahertz clock. So, you know, you can find it like that, or somebody will tell you it's called clock rate. So the clock rate is the same as clock. Makes sense? 500 megahertz. So if you are in this situation and you would like to know the duration of time for the cycle, for the clock, how are you going to do it? You flip this frequency 1 over of it, you get the time. That makes sense? Straightforward, right? Now it's telling you each instruction from ALU is taking 3 cycles, each branching 2 cycles, each storing 4, each loading 5. So see, instead of, you know, making this fancy table, you know, I made it written, right? And I'm telling you, I'm writing a program, and this program millions of instructions. 200 million of them is for the ALU, 50 million of them for the branching. You know, when I say branching and jumping, that means, you know, branch with condition, and jumping is basically branching with no condition, basically. 25 million, you know, storing data into the memory. You know, 20 million is picking data out of the memory and, you know, process it by the ALU. So the GPR, the general purpose registers, right? So the question, calculate this time the CPU time. This time I want what? The CPU time. That means how much time the CPU worked to make this happen, right? So solution for this, there's 2 approaches. One of the approach, just one shot, finish everything, which is what, you know, you say X is taking 3 cycles at a time. So X times 3 plus Y times 2, Z times 4, W times 5, the weight of the cycles. You know, you got the number of cycles. Here's my number of cycles. So I know for sure what is the number of cycles the whole entire program is taking. Do you agree?
Yeah, that makes
Then, you know, I see cycle. So I need the time of the cycle. I divide it by the clock rate, because, you know, T equal 1 over F and F 1 over T, right? So I know F, I need T. So that's why I said divided by clock rate, right? So gonna be 900-ish, whatever, time power 6 divided by the 500 megahertz. The value came 1.82 seconds. This is a good solution to solve this problem. There is another way. How can you do it? By the CPI. CPI, that means number of cycles per instructions, right? So here, CPI is what? X times 3, Y times 2, Z times 4, W times F, divided by what? How many instructions, right? So the branching and ALU and, you know, storing and loading, right? Add everything together. So the total came what? 3.03, right? Now I'm gonna use into the equation number of count instruction time that CPI divided by the clock rate, exactly as we did in the definition of the CPU time from the CPI, right? Then, you know, you just compensate values, the value will come out 1.82. So, you know, you can solve it by this way, you can solve it by that way. Does that make any sense? Okay, sounds good. Now, let's play a little bit.
actually, sorry, I did have a question.
You can have 2 questions. Go ahead.
So just so that I understood correctly, when you were calculating the CPI of 3.03, you just took the 3 clock cycles, the 2 clock cycles, 4, 5, and you divided it by 5. Is that right?
What's divided by 5? What? What do you mean? There is nothing divided by 5 here. See what happened. Look, when I tell you I need the instruction count, what is the instruction count from your point of view? Is X plus Y plus Z plus W, right?
Yeah.
This is all the number of instructions they have in the whole entire program. Do you agree?
Yes, I do.
Exactly. Times every single instruction has number of cycles. Do you agree?
Yes.
So the CPI, I calculate it, multiply all of this number, it will give me a value. I divide it by the clock rate, I figure out by the time.
Oh, okay. That makes sense. I see that.
Yeah. Okay. Anyway, another problem. Now, same thing. Have you noticed? Same story, but I changed for you the clock rate to be 1 gigahertz. Right? then here the program also has X value, Y value, Z value, W value. That means if I add all of them, that means all of the instruction in the program I know, right? I need to calculate the CPI and the CPU. Same thing I did here, I can do it here, right? Same thing. Basically, I know X and the weight per cycle, Y and the weight per cycle, Z and the weight per cycle, W and the weight per cycle, right? Calculate, divided by all numbers, I get the CPI, right? Same story. I count X plus Y plus Z plus W and time of the CPI divided by the clock rate, I can get the CPU time. It's just like, repeating the previous example, right? But with different values. That makes sense?
Yeah, that makes
Now we're gonna play a little bit. Now we're gonna we just warm it up. So now we're gonna be what? Suppose there is a program, and this program is called program A, and you ran it on the CPU time, but the CPU time is 3 seconds. Sounds good? And the elapsed wall clock time is 4 seconds. Now we need to return it back to the old lectures, right? CPU time, it means what? It means that's the CPU without IO, without memory, without anything, without operating system, without nothing, just CPU, right? Elapse, that means the system. That means it has IO, it has memory, everything, right? So CPU by itself taken 3 seconds. The whole entire system taken 4 seconds. When I say the whole entire system, that means CPU time inside it, right? Do you agree? Okay, look at this. The system performance is 10 M-flops per second. We know what does M-flops mean, right? Million of the floating point instruction per second. Do you remember that? We have MIPS and M-flops, right?
Yeah.
Assume that there are no other processors taking any significant amount of time, and the computer is either doing calculation in CPU or are doing IO, but cannot do both at the same time. By the way, this part made it easy. Can you imagine? So learn to read between the lines. So look here, assume there are no other process taking any significant amount of time, and the computer is either calculating CPU or IO time in the same time. What does it mean or not? It means that 4 equals 3 plus something. Again, that 4 seconds is basically CPU plus whatever, and that whatever is the IO. But if the system, the IO and CPU work at the same time, then you're gonna be in a little bit trouble. You have to try to figure out which one is taking the longer time to be the official time. So this sentence made it very straightforward that 4 equals 3 plus IO. That means the IO is what? 1 second.
Yeah, that makes sense. I see.
Do you agree, guys? Are you guys aware of what I'm saying or not? Hello.
Yeah, so you were basically explaining if they were working at the same time, the CPU and the IO, then the calculation would be much more difficult, right?
It's not difficult. I mean, a little bit tricky. That's all I do, right? Now, we decided to replace our CPU, the processor, and we put the new one running 6 times faster than the old one. And we left the IO as it is. That's why we said, doesn't affect the IO. That means the IO is still 1 second now, right? What will be the new CPU time? And what is the wall clock time? And calculate for me the M-flops, the new one. Because, of course, M-flops affected by the new CPU, right? So now it's easy, busy, lemon squeezy job, right? Which is what? CPU time of A over CPU time of B. It's a ratio. And we said the performance is 1 over the CPU time. So if I say CPU time A divided by CPU time B is basically I'm saying performance of B divided by performance of A. Do you agree?
Yeah, that makes sense.
Okay. Now we send the new processor is 6 times faster than the old one. Do you agree? So that means 6 equal the 3 divided by the new CPU time, which I have no idea what is this, right? So now it's a straightforward that, the new CPU time will coming out of this equation will be what? Half second. So the old one 3 seconds, now this one half second. Do you agree? Then I need to calculate the elapse. Elapse is easy, is IO plus the CPU time. So I know the I will never be changed. It's gonna be 1. 1 plus that half is gonna be 1.5. Sounds cool?
Yeah, that makes sense.
Okay. Now, how are we gonna calculate the new M-flops? It's not very hard, right? It's really piece of cake. Why? We'll say system performance of the M-flop is basically number of the operation of the floating point time 10 power 6 because it's million of instruction divided by the whole clock time. The whole clock time for us is what? Is the 4, right? Here, the old one is 4, right? Old one is 4. So basically, it's gonna be what? It's gonna be the old equal this 10 power 6 divided by 4. So from there, I figure out what is the number of the floating point operations happening. Do you agree? Then I need the new. The new is what? Is that value, but divided on the new world clock time. What is the new world clock time? 1.5. So that value divided by 1.5 is gonna be what? 26.667. Is there any question so far regarding this?
Yes, Professor, I do have a question. Where did for the old system performance you had number of floating point operations, but how come it's 40 times 10 to 6? Or is it just because you divided by 4?
No, think about it. This equation, it has a numerator and denominator. Do you agree?
Yes.
Okay, so I'm telling you my system is 10 M-flops per second. How did I calculate this M-flops per second? I said it's basically number of floating points operations, right? Time 10 power 6 divided by the walk clock time. This is equal what? 10 M-flops per second. Do you agree?
Okay, I see that.
Yeah, so basically I just put 10 equal this number of operation, which I have no idea what is this, right? Divided by 4. I sent 4 there and I 10 power 6 there. I figure out what is number of floating points, right?
Okay, I see that. Yeah.
Then now the whole clock time it changed. Okay, I take that number divided by the new whole clock time. I figure out the new flops.
Okay. Oh yes. Okay, I see that. Yes. Yep. That makes
sense.
Yes. Yes, it does.
Okay. Any questions so far regarding this part? Hey guys, is it clear? Easy busy?
Lemon squeezy.
Okay, perfect. Okay, now we're gonna go in another example, right? Let's say that we decided to build a team. That team will design a new processor. Let's say Cal Poly Pomona decided to build a processor that will compete with Intel, right? And you came into your knowledge and you built the processor and it made it run with a Crystal 200 megahertz. And then while the people in the team benchmark for you this processor, you find out that if I run any program, 30% of it will be load and store. That means it's stuck into the memory, and 50% it will be arithmetic. That means add and subtract and multiply and logic and whatever. And anything else, which is basically the IU and branching at 20%. And we figure out that those 20%, the penalty in cycles, 3 cycles every time, the other one 4 cycles, 6 cycles. Sounds good? calculate for me the CPI for the benchmark made this table. Straightforward, right? Huh. It's not very hard. The solution is the following. I can assume, to make it easy, right, that I have a program running 100 instructions. So my program is running what? 100 instructions. This is my assumption, by the way. If you make any assumption, it will work. That makes sense? But I made it 100 to be easy. Somebody will tell me why you made it 100. Then I can say, what is 30% of 100? What is 50% of 100? What is 20% of 100? So it will be a number easy I can put, right?
Right.
So basically, I made assumption. I said, assume and then 100 instructions. Then I came that, okay, go ahead and make what? 30% of the 100 is 50. 50% of the 100 is 50. 20% of the 100, 20. So now I made it what? As a number, right? Then I start multiplying and adding, as I mentioned, right? You start adding with weight, divided by all numbers, which is 100 in this case. And then, you will come out into the point is what? 4.4 cycles per instruction. So far, what I said makes sense?
Yeah, it makes sense. I had a question, Professor.
Sure.
Could we just directly multiply the frequency in cycles and get the CPI that way? So for example,
It can, but don't forget those are percentage, right?
right. So it'd be like 0.3, 0.5, 0.2.
Yeah. We did that before. Do you remember?
Oh, right. The first example, right?
You forgot.
Okay,
we
that
did it in
makes
the top, right? Yes. Anyway, now the second part of the problem. See, the CPU execution time on that benchmark is 11 seconds. This is the CPU time. What is the native MIPS processor speed for the benchmark in millions of instructions per second? What does it mean from your point of view? It means that I need MIPS, right? I need MIPS. You know what MIPS, right? It's a matrix. It's not MIPS, our microprocessor. So basically, MIPS clock rate divided by CPI time 10 power 6, right? So in that case, I can put my 200 megahertz. I can put the value of 4.4. I can do all of this. So the value came what? 45.45, 45, 45, 45. And we know that MIPS doesn't have what? Unit. It's just units, right? Just numbers. Do you agree?
Yeah, that makes sense. I see.
Okay, now the processor performance, okay? What I wanted to look for, I don't know what happened. Okay, now we start adding something. So the hardware expert people in the team who build the processor, right, says that if you double number of registers, the cycles time must be increased by 20%. Again, so we decided that we are risk, and that's GPR. I decided to double number of registers, and instead of 32 registers for let's make it 64. And we made circuit analysis before, and we figure out if we increase the GPR, the multiplexer for selecting, it will be much bigger. Then what will happen? The critical path will be extended, right? Which is basically what we said here. The cycle, it will be stretched 20% more, right?
Yeah.
That makes sense? So, if you want to calculate the new frequency, what you're going to do, you will bring the old clock rate, you flip it, you get the time. Then you add 20% on that time and you flip it again, you will get the new maximum frequency, right? Do you agree?
Right, because that was the old clock rate. Yeah.
This is the only solution, basically. Anyway, so here, the clock time, 1 over cycle time. and then, sorry, the clock rate. So basically 1 over the 200-ish, whatever, it gives you time, right? Then you multiply that time by 20% and you add it to the 100%, right? That means you multiply this with 1.2, basically. 1.2 times this value, it became like that. Flip it, so you can read it in frequency, right? Flip it, it will come back to 166, whatever. So the price of extending the GPR to the double cause you to lower the frequency from 200 megahertz to 166.6667. Correct?
Yeah.
Okay. Now, compiler people, software people got mad. And so now we see what they're gonna get. So the compiler expert says, if you double the number of registers, then the compiler will generate code that requires only half number of load and stores, which is correct. If you increase the GPR, you don't need to talk to the memory that much, right?
Yeah.
So basically, yeah, you increase the duration of the clock 20%, but you decrease number of talking to the memory to the half. When I say to the half, that means I will go back here. That was load and store 30%. Now it's 15%.
Yeah, that's a pretty big increase. I see that.
Exactly. So it's no longer 100 instruction. It's gonna be 85 instruction. Right? Do you agree? You remember when we said, and I consider them 100. Now, we said they're gonna be 15%. So 15%. So it's gonna be, instead of 30, gonna be 15 instruction just for load and store. And the 50 as it is, 20 as it is, right? Because it didn't affect that much by the increase in the GPR, right?
Oh, actually, yeah, I had a question about that. So the
You
load
can
and
ask
store
questions.
got reduced to 15,
Hmm,
but the other frequencies did not get affected. So it's still 50 and 20. Right?
exactly.
Okay, that
See,
makes sense.
we are playing now, it's cool to play, right? Okay, what would be the new CPI? Of course, the CPI will be changed, right? Because you decrease number of something, right? So since we already agreed that we have 100 instructions, and we agreed that the 30% became 15%. So now gonna be 15 load and store, 50 arithmetic, 20 all others, right? To get the new CPI, you're gonna multiply, right? This to this to this to this, divided by what? Instead of 100, it became 85, right?
Yeah.
Which is gonna make it what? 4.12. 4.12.
And that's
So
faster
what?
because that's lower, right? Lower cycles per instruction.
So basically, what happened? Your CPI went from 4.4 to what? 4.12, which is not bad, right? What is the best number of the CPI can be? 1.0 maybe. Yeah, it is 1.0. It's not maybe, it's for sure. You know what I mean? Okay. Now we're gonna add more fun stuff, right? How many CPU seconds? That means I'm looking for CPU time, right? Will the benchmark take if you double number of register taken into account both the changes described above? That means that 20% increases of the cycle duration, which is gonna flip into the maximum frequency to be 166 megahertz, and the compiler people, which is flipping into the CPI to be 4.12. Calculate for me now the new CPU time, basically, right? So how you're gonna do it is just like applying some stuff, right? Here, CPU time, number of instruction for whatever clock rate. So first thing we need to do is calculate the number of instruction which is execute in 11 seconds. Somebody will tell me why 11 seconds? Because in the beginning we said the CPU was 11 seconds. Do you agree?
Yeah, that was for the old benchmark.
And we calculate before the MIPS, and it was 45.45 something, right?
Yeah.
So basically, end of the day, what we are doing, we're trying to get number of instruction again. And from there, we can apply by multiplying the percentage of the load. Do you remember it was 30% in the beginning? Do you remember? And from there, we can remove the, instead of the 30, it's gonna be 15, right? And also you're gonna apply the new clock rate because you already have 166667, right? So end of the day, the number will come to be like that, which is 10.548 seconds. So all of the changes we made, which is basically doubling the register space, that it increase the clock's duration and decrease number of load and store by half, it's gonna make you, end of the day, instead of executing in 11 seconds, you will execute in 10.548 seconds. Cool, right? That shows you not every single thing that it run in a maximum frequency low, it will be nothing, it will be impacted. You might actually, end of the day, actually run in a small amount of time, right?
Yeah, that makes.
So far, guys, whatever I mentioned, clear? Alexander, Alex, rest of you guys, Raymond, Jason, everything's clear. Okay, good.
It's clear.
Super. I can tell you this last two slides here is just talking about how can you understand the load word and store, which is chapter 2. And I already described this to you many times. Do you remember? This one for the load word, right? I told you this is the offset 16-bit, this is the base 32-bit, and then you know this is the location that it will be loaded from the memory with data. Do you remember that? An example in front of you, like, you know, here is the address in the memory. From where you're gonna get, you can say that, you know, 10 is the base, and that part is the offset 60. And the value will be coming out of the memory loaded there. That's it. And I can say that, you know, we finished the examples I wanted to show it to you before you will go for your midterm, sorry, the quiz. Any question?
Professor, the quiz is just over chapter 1, correct?
Yes. So again, chapter 1, quiz 1. Chapter 1 and 2, midterm 1. Chapter 3, quiz 2. Chapter 3 and 4, midterm 2. Final 5 chapters, all of them.
Okay, thank you, Professor.
You're welcome. You guys have any questions? No questions? I can tell you that I finished for today, so try to do your best, and you know, I'll see you Monday. I will work on loading everything on the grid scope and, you know, put it on the what's called canvas, and I will have it with a timer, so it will be released by the time of the exam. So you guys will solve everything, put it there, and I will be meeting you in person on Monday. Thanks so much, and have a nice weekend.
All right, sounds good, Professor. Hope you get better. Thank you.
I
God bless.
appreciate it. Thank you. God bless you guys. Bye-bye.
Bye.
Thank you.